November 18th, 1987. King's Cross Station, London. Rush hour crowds fill the underground when a passenger spots something terrifying glowing beneath an escalator. It's a fire, small, seemingly manageable, burning quietly inside the old wooden Piccadilly line escalator shaft. But something is already deeply wrong. London Fire Brigade units arrive within 10 minutes. The escalator fire looks minor, the kind of call they've handled dozens of times before. Then, without warning, the entire shaft erupts. A massive jet of fire blasts upward and punches directly through into the main ticket hall above. In under a minute, the ticket hall becomes an inferno. 31 people are killed, the deadliest peacetime disaster on the London Underground. What turned a small, smoldering escalator fire into a fatal fireball? Investigators would spend 7 grueling months searching and find something nobody expected. To understand what happened at King's Cross, you first need to understand how fire investigators actually work when they arrive at a major scene. Most large fires don't destroy entire buildings. Firefighters contain them early enough to leave behind a scene rich with physical evidence and burn patterns. Investigators systematically narrow the search from the full building down to one room, then to a single object, by reading how the fire moved. Fire burns upward and outward. When it ignites beside a wall, it deposits a distinctive V-shaped scorch mark that widens as it climbs toward the ceiling. An object set further from the wall creates a broader, rounder U-shaped burn pattern because the flame tip never actually reaches the wall surface. When a fire is suppressed early and stays small, these char patterns act almost like directional arrows pointing straight back to the origin point. But once fire spreads across multiple objects, those patterns begin merging together, making the original source far harder to identify with any certainty. Fire also pulls toward open doors and windows where oxygen concentrates, leaving those zones looking more severely damaged than the actual ignition point. If arson is suspected, investigators can deploy specially trained sniffer dogs capable of detecting accelerant residue like gasoline even after heavy water damage. Another key technique involves measuring char depth, the carbon layer left as material burns inward. Deeper char means that spot ignited earlier in the fire. Comparing char depths across a space builds a map of where burning began first, guiding investigators backward through time toward the true ignition point. These methods work reliably when fire behaves predictably. But the King's Cross fire broke every rule investigators had ever relied on, starting with direction. Eyewitnesses described the flames moving nearly horizontal, clinging to the escalator steps at a steep angle instead of rising upward like any normal fire. This was completely unprecedented. Fire investigators had never seen flames behave this way. Their existing models offered absolutely no explanation for what witnesses described. Before explaining the behavior, investigators needed to trace the origin, starting in a station where smoking had officially been banned for some time already. In the 30 years before King's Cross, more than 400 separate escalator fires had been recorded across the London Underground network alone. Despite the ban, passengers lit cigarettes just before the escalators. Burning matches and cigarette ends fell through gaps between the old wooden steps constantly. Those wooden steps were a critical factor. In 1987, King's Cross escalators were still built with the original pre-war timber construction, not modern metal. These small fires almost always extinguished themselves. So why did this one explode catastrophically when over 400 others before it had simply burned out? When investigators opened the other escalators at King's Cross, they found thick dark grease coating the mechanical components, untouched by cleaning crews for years. Alone, the grease resisted ignition, but years of accumulation had packed it with dust, lint, and debris, transforming it into highly combustible material. Lab tests confirmed a burning match dropped through the gaps could ignite this contaminated grease almost immediately, recreating the exact conditions of November 18th. But on an open-air model of the escalator, the fire burned vertically and died out normally. Whatever caused the explosion in the real shaft was still missing. One theory pointed at the ceiling, 20 accumulated layers of old paint. Investigators suspected this thick, aging coating had ignited and spread the fire upward. The fire never touched the ceiling. It stayed pinned to the escalator steps the entire time, disproving the paint theory entirely. Investigators needed a completely new approach. They turned to Britain's Cray 2 supercomputer, one of the most powerful machines on Earth, to simulate the fire. It was the only Cray 2 in the United Kingdom. Scientists programmed it to calculate temperature gradients, airflow patterns, and gas dynamics inside the escalator shaft. The simulation calculated temperature and airflow at multiple points throughout the shaft, modeling the precise conditions present on the night of November 18, 1987. The results stunned the research team. The computer predicted exactly what witnesses described: flames hugging the escalator steps at an angle rather than rising upward. By every known principle, hot gas rises vertically due to buoyancy. The simulation showed the opposite: gases forced along the angled floor of the enclosed shaft. The answer was the shaft's own geometry. Its narrow, trench-like channel, combined with a 30-degree slope, fundamentally altered how heated gases were able to travel straight up the escalator. Some flames initially escaped upward through the gaps between steps, but most were channeled beneath the wooden treads, accelerating upward through the fully enclosed shaft. As the gas stream accelerated, pressure dropped, creating a pressure differential above and below the wooden steps that actively dragged the fire flat against them. This gradually forced the fire flat against the underside of the steps. The faster it burned, the faster it traveled, locking the flames completely in place. From above, passengers saw only a small, apparently harmless fire halfway up the escalator, completely unaware of what was happening directly beneath the wooden steps. Beneath those steps, superheated gases were cooking the entire wooden escalator structure to temperatures well exceeding 500 degrees Celsius along its full length. Those scorching gases funneled upward into the ticket hall, filling the void above the false ceiling with enormous quantities of superheated, highly combustible material. When materials reach a critical temperature from absorbed radiant heat alone, without direct flame contact, they ignite spontaneously. This catastrophic event is called a flashover. At King's Cross, the escalator structure and surrounding gases reached that critical flashover threshold simultaneously, and every surface in the ticket hall ignited at once. A fireball erupted up the escalator shaft and blasted into the ticket hall, igniting every surface, every fitting, every person caught inside within seconds. The Cray 2 simulation had predicted this exact chain of events with precision, but demands for physical proof meant investigators still needed to test it in reality. Investigators built a physical scale model of the escalator shaft. A controlled fire was set at the base, and the team carefully recorded exactly what developed. Initially, the fire burned exactly as expected, vertically upward, following the conventional rules every fire investigator had been trained to understand and predict. Within a few minutes, the fire began to tilt. It slowly lay down and hugged the floor of the model, confirming precisely what the Cray 2 had predicted. This phenomenon was officially named the trench effect, a brand new discovery in fire science born directly from the worst disaster in underground history. The findings triggered immediate safety reforms. All wooden escalators were removed. Heat detectors and automatic sprinkler systems were permanently installed beneath every shaft.